We've connected the buttons to the set and reset lines. So then set and reset the latch. Here we have a simple circuit emulating the current mode control with the current feedback voltage simulated by this capacitor just to have a larger time constant. If we send a clock pulse, it sets the latch and it only resets once the capacitor is at the desired output voltage. Turns on for a second while it charges the capacitor and then turns back off. If we periodically apply the clock signal, the output voltage hovers around the target value. Here we can now see the voltage readings on the oscilloscope. If we cycle the clock, we can see the RS latch turning on and the capacitor voltage is charging up. And as soon as it hits the target value, it turns back up and the capacitor voltage decreases again. If we activate the clock periodically, we will have a regulated signal. We now apply a periodic pulse and we can see the voltage going up and down. Every time the purple trace applies a pulse, it turns on, rises to its level and then falls back down until the next pulse comes. We have now set the set point to 1 volt and we can see the pulse is getting a lot more narrow. And we can see the voltage across the capacitor getting regulated around the 1 volt mark, seemingly going between 0.9 and 1 volt. This is a type of charge pump as it uses a capacitor instead of an inductor to charge power. These are typically not used in practice. We've now increased the switching frequency to 20 Hz. And reduced the series resistance. We can see now the output voltage is very stable. So now we can see it reacting closer to real time to adjusting the set point. Here we can also see a problem of sub-harmonic oscillations, of cycles not perfectly repeating each time. This mainly occurs above 50% duty cycle and is a known problem with this type of controller.